Here's the homework for the torque, or the answers to the torque homework, and you'll see that I screwed one up. So problem one is very similar to something that the example I did in class. I'm on one side, grandma's on the other. Clockwise torque, counterclockwise torque for me, clockwise torque for grandma. Net torque is the subtraction of the two since they're going different directions. Just like if we had a force going to the right and a force going to the left, we subtract those. If the forces or torques were going the same direction, we'd add them. For number two, we're asking where should grandma move in order for us to balance out. So since she's heavier, she's got to move in closer. So in that particular case, then, I'm going to use my torque counterclockwise equals the torque clockwise. That's the extra torque I had, or pardon me, that's the counterclockwise torque I had, so I need the clockwise torque to equal the same amount. So I put her weight and figure out that second distance. And that distance, though, is from the fulcrum, which is at 6.5 meters. So if I add this amount to 6.5, that'll let me figure out where she should be on the seesaw. Number three is figuring out the weight of the meter stick. Key thing here is you have to think of the whole meter stick, and its center of mass is at the center. So that means it's 50 centimeters, even though you'd say, well, wait a minute, this is only 90 centimeters to the right of this fulcrum. Wouldn't the meter stick's mass be acting halfway from here to the end? It's not, because we have to take into account the fact that there's some part of the meter stick on the left side. So the nice thing about the center of mass is, once you know that for that object, it's still going to stay the same unless the object changes. And so therefore, it'll be at 50 centimeters. And that's 40 centimeters from the fulcrum when it comes to our calculations, which I've got those over here. Number four was the one with the bridge. I screwed it up. Even though this was 400,000 newtons as the weight of the bridge, for some reason or other, I ended up putting mathematically that it was 200,000. So that screwed me up. So I fixed it thanks to the miracle of whiteout, but it looks messy. So that's exactly why I actually do all the homework that I assign, so that I can sort of figure out where I might make mistakes, where you might make mistakes. So we've got these two big ideas. Force up is equal to force down, and torque clockwise equals torque counterclockwise for an object that's both in translational and rotational equilibrium. So the force down adds up to 4.196 times 10 to the fifth newtons. I pick my left bridge support as the pivot point. And so this car would cause a clockwise torque, the weight of the bridge would cause a clockwise torque. The force upward on the right side would cause a counterclockwise torque. So if you notice this, counterclockwise, 17 minus 3 times this equals the weight of the car times its distance, plus the weight of the bridge times that distance from the fulcrum. So when I do that, I figure that the force on the right side is 2.028 times 10 to the fifth, or 202,800 newtons. If I know the total force upward is 4.196 times 10 to the fifth, I subtract the force of the right down. That leaves me the force pushing up on the left side is 216,800 newtons. 5 and 6 are very similar both to each other in the example I did in class. So for 5, I picked the left side as the pivot point. Again, using these two equilibrium equations, total force down was 1,240 newtons. Counterclockwise torque caused by the rope on the right. Clockwise torque caused by all those masses acting downward. And there's a bunch of them. That gets me the force on the right is 527 newtons. If I take 1,240 newtons and subtract that force on the right, that gets me now 713 newtons is up on the left. Finally, number 6 is very similar. At this point, I chose the right end as the fulcrum just to be a little different. And remember, when you're doing the math, you always have to measure the distances from the fulcrum. So, for example, this force is acting at 3 minus 2.5, or only 0.5 meters. So when I do that, again, F up equals F down, torque counterclockwise equals torque clockwise. I end up getting the force on the left end is 1,006 newtons. The force on the right end would end up being 1,589 newtons. If this rope was replaced by something at a 45-degree angle. Hey, let's see if I can figure out how to do that. So with something like this, should be a line or an arrow. There we go. Nice. So something, oh, that's awful, like this, then if I would need the same amount of torque as when this thing was pulling upward, so therefore I'd have to pull at a larger force to gain the same upward component. So essentially, this length of this arrow is longer than the length over here, even though they have the same amount of vertical force. So that's the conceptual understanding of that. Anyhow, hopefully this makes sense. Torque is something people usually do pretty well on.